So today, second part of chapter 3 about heaps and paths, flow, and rearrangement monoid. So just I recall you from the previous lecture what we have done. So we have defined the flow monoid. The alphabet is pair of element of x, which is denoted like this. And the basic piece is the alphabet. The commutation monoid is two element commute if and only if the initial vertex of the edges are different, or dependency relation. Complementary means that two edges are on the heaps of one another if and only if the initial vertex are the same. So element of this flow monoid is denoted as a byword. The letter is noted like this, ij, and you take the equivalence class of this element and you get a flow. Maybe it's not a good vocabulary, but that I follow the vocabulary of Cartier and Fouatin. So you can also see this as a in the space as a heaps of half edges. The edges is the edges, or I should say arrow-oriented edges, and the dependency relation, if and only if they have the same initial vertex. So you can see any flow is decomposed into a direct product of all the edges starting at the same point, so it's a direct product of free monoid. And if the alphabet, if x, the underlying set here, x equal 1, 2, 3, if x is totally ordered, then any elements of the flow you can uniquely represent like this when you put in total order the first line of this tableau. So you put all the 1, all the 2, all the 3. So you see an edge starting with 2 and an edge starting with 3, they commute. But inside all edges starting with the same point, they don't commute. So this is flow. And then we define from a path how a path can be viewed as a flow. So a path is just a sequence of points S0, Sn in any set X, S0 initial point, Sn the last point of the path. Usually we will put a weight on the path as a product of the weight of the elementary step. Elementary step is a pair of two consecutive vertex, and the weight will be monomial or formal polynomial, informal variable with some integer coefficient, and the canonical weight will be Aij, where Aij is an element of the matrix, a k by k matrix, if the set X has k element, and Aij will be considered as formal variable. After, if you are probabilist, analyst, or physicist, you will replace Aij, but your favorite thing is a complex number or a polynomial or anything you want. Then any path in X can be viewed, you have seen, as the heaps of half edges, the heaps of arrow. So you take this path and you just cut, you see, you take it as a flow. So you get this. Each edges, you see, imagine then you just remember the first part of the edge. You know where the edges is going, but you forget in which exact order all the edges were from the sequence of the path. So I call this f of omega. It's like breaking the edges. You have something, picture like this, and I claim that we can reconstruct the path from this image f of omega. So you don't lose any information. You can reconstruct as soon as you know the initial point. And to reconstruct, we have seen that from this flow, which came from the path, we have seen an algorithm following the flow. So remember, following the flow, you have any general flow, even the flow not coming from a path. You start from a vertex, and then you follow the edges like this, an algorithm, in the order they come, order from the initial vertex. So you start from this, then initial edges on the floor tell you to go to 2, then you take the lowest of the edges coming, and then you 2 go to 3, etc., etc. So you go like this, and after, in this example, then you are at the point 6, you are finished. Because there is no more edges to get outside. So maybe in black, you see there remain some edges in the flow. So this was very easy algorithm. Then the fundamental definition of this chapter is rearrangement. Rearrangement is a flow such that there is the same number of edges getting inside the vertex as number of edges getting outside. So it defines the external degree of a vertex for a flow. Total number of edges going outside, d minus total number of edges getting inside, and rearrangement means that these two numbers are exactly the same. And rearrangement are a submonoid of the flow monoid. If you take the product of two rearrangement or the product of the heaps, then there will again be a rearrangement. And the main theorem is that rearrangement is equivalent to a heaps of cycle. So I remind you some vocabulary because according to the, if you have in graph theory, in combinatorics, in different fields, the vocabulary is changing. So to fix the idea, I will say a path becomes a circuit when S0 equals Sn. A path going back to the origin, I will call this a circuit. An elementary circuit is when all the vertices of the circuit are disjoint except the first and last one. So usually people call this elementary circuit, and I will call cycle elementary circuit up to a permutation of the vertices, which means that you forget the initial point. So this is the image of a cycle, and I will be a perverse person to tell you that I will sometimes use the word pointed cycle, because I will have many cycles, and then if I put a point, pointed cycle means exactly coming back to elementary circuit. But if I say pointed cycle, it will be the same as elementary circuit. So I say cycle because in all combinatorics of permutation, this is a cycle notation of a permutation, and we say also, we say that all these are cycle. We don't say that this is elementary cycle, all this is cycle. So in all the class, cycle means in other language, sometimes people call this elementary cycle, and they call cycle a circuit up to a circular permutation. This is a different vocabulary that maybe we will use it when we will work with zeta function on the graph. So this is fixed, and now we have the heaps of cycle monoid. So the basic pieces are cycle on the set X, like this. The dependency relation, two cycles are dependent if and only if the underlying set has a common vertex. I call the underlying set of vertices the support of the cycle. And if the support, it's intersection non-empty, then I will say the two cycles are dependent. So this is a competition relation, and then the heaps of cycle monoid, it's all the heaps you can get by putting a product of such a cycle. So this is the heap, you see. You put one over another. This product means product of heap. So I put the cycle one over another. And then again, I define the function f, breaking the cycle, analog of function f for the path. When I break, in the past, I know the succession of the edges. When I break them, I just remember the first point, and I know where it's pointing. But I break the edges, and I don't lose any information. So I have the analog map. F of E is the product of the f of the cycle. F of a cycle, you break the cycle. So you say you lose some information when you have a heaps of cycle. It's become a heaps of edges. So you go back to the flow, and I claim that I can reconstruct the heaps of cycle. So proposition, this map is a bijection, is an isomorphism between the monoid heaps of cycle monoid and the rearrangement monoid. And last time we have constructed the reciprocal function G. If you have a rearrangement, how to reconstruct, to reglue the cycle together. I call it a gluing bijection. You have small pieces, half edges, and then you are going to glue them together to make big pieces, cycle, which are going to be in competition each other. The whole cycle will be in competition with another cycle. So this is the images. You have this is a heaps of cycle, and imagine you break all the cycle, you cut for each point of the cycle, so all the half edges are falling down, and then I claim, so you get a rearrangement in the sense of a subset of flow, and I claim I can go back, reconstruct totally the cycle. Example. So last time I had this example, you see, it's so here is a rearrangement, because you see there is a number this by where there is 3, 1 on the top, and on the second row there is 3, 1. So there is 3 edges going outside of the 1, and 3 edges getting inside. The 2, there's 2 edges going outside, and 2 edges getting inside. And the 3, there is 4 edges getting outside of the 3, and 4 edges getting inside. So if I just like look this, I must reconstruct, it must be in bijection with the heaps of cycle. Here is a heaps of cycle. So the easy exercise, do the algorithm following the heaps. Start from 1, start from 2, or start from 3, and you will get always the same heaps of cycle. So this was the bijection I explained briefly last time, that if you take a rearrangement, you take any vertex, follow the heaps of edges, follow it, and then you will be never stop, and then you go back to the origin. And if you are going back at the end when you are stuck, means in fact you get a whole rearrangement. Maybe it's finished, and maybe there is some other cycle on the top. You continue to do your following algorithm with another vertex, etc., etc. And then you decompose your whole flow into a heaps of cycle, and I claim that this cycle you get are unique up to the commutation motion or up to the dependency relation of heap. But maybe to make more clear, I will make a variation of this proof. I will give a second proof, maybe more easier. It's almost the same, but as it's a fundamental lemma on this class, that's rearrangement equal heaps of cycles, so it's good to have 2 different proofs. The proof is the following workshop experiment. If you have a heaps of edges, what do you see above a general flow? If you look above a flow, what do you see? Or below? Below is the same, because up or down. And what do you see above a rearrangement? Homework, exercise. We do it now. So what do you see? It means if you look above, there is some half edges. You can see at the maximal half edges. There is nobody above the half edges. And what you see, so you take all the maximal half edges, maximal in the sense of the flow of the heap. And then you look, what is this combinatorial structure you get? What do you see? And you see this. So see these edges in blue or in red. They are the edges which are at the top, maximal pieces of the flow as a heap of arrow, of half edges. And in green means there is some other edges, but the starting point is below this point. See here, maybe there is many. So so you see the vertices. Vertices, you see. So you see on each vertex there is many starting of edges, many half edges, many, and above on the top, the edges may be blue and may be red. So the red edges mean if you follow these maximal edges, you get a cycle. And also there is some blue edges. See, if you follow the blue edges, it's fall down on a cycle. So in general, if you take any maximal edges, just follow the edges. Then if you have another maximal edges, you follow, and suppose you start from this, for example, you follow, then I follow, and then I get a cycle. Maybe I don't get any cycle, but if I get a cycle, then you get this picture. So you have a certain set of cycle, and on the cycle there is a certain set. What are these? This is trees. You have some trees, pointed trees, because the trees has a certain root. It's an arborescence, and the arborescence, the trees, is rooted, is fixed on some cycle. Maybe there is no cycle. Maybe there is 3 cycles, and maybe see there is isolated tree. This tree, then it stops. There is nobody here. So this is a general picture you see above a flow, or below it will be the same with minimal edges instead of maximal edges.
Trees usually have the opposite direction.
Well, this is a direction because I follow the edges. Okay. No, each arrow, I am in the flow. So an arrow is a pair, S going to T.
Trees usually start from the root and then...
It depends. of the way of thinking. In some country, well, it's some country you are driving on the right, some country you are driving on the left. Some country we are driving on all sides of the road. It's, if you go to Europe, to China, or to India, then so it's depends of the. So everything is right as soon as there is no accident on the road. So let's go back to the picture we have seen is the endofunction. So I claim the maximal edges, they form an what we call an endofunction of y. Y is the support of the flow. The support of the flow is all the set of vertices which are covered by the starting of an edge. So here see the support is all this point which belong to the initial point of the vertex. So this is in the support, maybe this not. It's not the support, is just the starting point of the edges. So if you project it on the ground, then you get a certain set. I call this y, which y. It's all the set of vertices of x, which are covered by the flow. Covered means that there exists a t such that st belongs to f. And
one minute. You told
yes.
that blue edges means it will point at the end. It will reach a cycle.
A cycle or nothing.
Triggers.
Or it will stuck.
Stuck. So then, what is the difference between green edge?
The green is some edges which are not maximal.
Okay.
Here is nothing because there is nothing. No edges getting in, no edges getting out. Here, maybe here there is two edges. Here, for this point, there is some green edges coming from this point and going here. But in this point, there is no edges starting from this point. Because as soon as there is an edge starting from a point, then there is a maximal edge starting from this point, so there is a blue or a red edges above it.
But it won't be an endofunction of y, right? Because, I mean, like in your picture, that isolated tree,
Endofunction means it's you send yes, it's
y to x.
It's y to, yes, y to x. Okay, I have a slight correction to do, yes. Because this point does not belong to y. So it's let's say it's a partial endofunction of x. Partial means it's certain point of x are sent on some other point of x. Thank you for the perspicacious remark.
Can you just say one more time what the blue edges are?
So the red edges is edges which form a cycle. And the blue edges are all the other edges which does not form a cycle.
Maximal edges.
The blue and red are maximal edges. I am looking what I see on the top of heaps of a flow. What I see above means I see only the maximal piece. Maximal piece means the edges, it's arrow, I would say, which are on the above. So, which means that you can see the starting point of the edges. There is no other edges starting above this. And then you go to another vertex, but maybe there is several people going to this vertex. I don't know which one is above the other one. Because of the commutation relation, the dependency relation is only two edges are dependent if and only if they have the same starting point. But you don't know when they come to the same vertex, you don't know which vertex is above the other one. In fact, there is no order. There is no competition between vertex starting from two different points. Right? They are independent. In each of this vertical line, everybody is independent of the other vertical line. But when I glue all vertex to get a heaps of cycle, now there is some dependency, very strong dependency between everybody.
So green edges are all the other edges?
Yes, all the other edges. So I repeat, the color edges, blue and red, are maximal edges. The red are edges which form a cycle. And the blue are color edges, maximal, which are not in a cycle. So a loop, if you have a loop, then the red cycle is reduced to only one point. To a loop, it's possible to have loop. And I claim that a rearrangement is, lemma, remark, a rearrangement if and only if there is no trees in this picture, in the endofunction. Only cycle. Why this is not a rearrangement? Because if you have a tree, then there is some point starting, there is some leaf, like this point. Right? When you follow the flow, you start from this. In this point, so one edge is getting out. And I must have the same number of edges getting inside. Maybe there is several edges. Below the blue, there is several edges getting out. But I must have at least one edge getting inside. But if an edge gets inside, there should be a color edge above it. So there should be something blue or red coming inside here. So there is no such point. There is no leaf in the tree.
No, but there's a colored edge above it means there's only something going out from where it came, not.
But in this point, an edge should come inside. In the leaf. You see this point here? An edge is getting out. So you must have an edge getting inside.
But it may be green.
It must be blue or red. Because if an edge coming inside, I have a.
It may be coming inside from some
But you
point.
have,
from
you have a
which-
point. There may be a green edge coming inside.
But it is under
But
some
there should be
other.
some
Yes. I am wrong.
There may
Yes.
Well. So exercise it.
But if it's a rearrangement, at least it's an endofunction of y is clear. Because
So exercise, prove this. It's because if you have the same number of edges, so there maybe another edge is green coming inside. So if this green edge is, for example, this one coming inside, so it must be a point
For
where there is
example,
some maximal edges. It must be a point where above this point there should be a green. There should be a green, or there should be a blue or red edges.
For example, that green
This
edge
point.
down,
Here?
down. Yeah, that green edge.
Yes.
So that is covered by the blue edge on top.
Yes.
But in a rearrangement top layer, we must have cycles. One
No,
layer.
That's the lemma. In a rearrangement, there is only cycle.
In the top.
because
On the
we
top.
already know it's a heap of cycles.
No, don't forget, it's a heap of cycle. Also, if you are stuck here, if there is nobody coming outside, if you are stuck, then it cannot be a rearrangement. One edge is getting inside and nobody is getting out. So if you have a blue edges with stop,
Yeah.
not a stop on the cycle, then it cannot be a rearrangement.
That is true. So maybe you have to look
So
at the
why?
other edge. Maybe it's not this edge, but that edge. That one. Yeah. There maybe.
Yes, maybe this one, because there is one edge is getting inside.
Yeah, and there's already something going out. And
Yes, already something getting out. So everything here will be because if there is another edges getting inside, so there will be maybe two blue edges getting here. So maybe there are several blue edges getting here. So there should be the same number of edges getting out. Well, it's maybe not so trivial. So I leave you as an exercise. But at least if you have now I can say, if you have a rearrangement, there exists some cycle. If you have a rearrangement, because if there is no cycle, all these blue trees will stop somewhere. And if they stop, if the blue tree stops, then this cannot be a rearrangement because the edges are getting inside this last point and no edges is getting out. So after I finish so in a rearrangement there must be some cycle. So to take one of this cycle, delete it, and once you delete it, the property to have same number of edges getting in and out is preserved. So below it's again a rearrangement, and you continue recursively, and your rearrangement become a heaps of cycle. And then when I finish, then I cannot see any trees, so I have proof the exercise in an indirect way. But it's
Not so clear actually.
yeah, it's not so clear. It's
No, maybe that's not true.
maybe it's not true. So exercise, second exercise, disproves this property. Maybe it's not true. Yes, if you have a rearrangement.
Rearrangement means products of cycles.
Yes. Okay. So I have proof. Let's go to the class to continue because I have a lot of material today. Sorry. So, okay, if you have a rearrangement, you are convinced that there is at least a red cycle on the top. You delete it, you have a rearrangement, you go like this, and then you get a product of a cycle.
It's by induction.
And this product by induction, recursively. And when you have this product of cycle, you break the edges, you get back a flow, a rearrangement, and then you can prove that this product is unique up to a commutation of the cycle. Because if you do the reverse, if you take all the cycle on the ground level, if you take the ground level, there is at least one cycle, then you delete all the cycle at the ground level are totally determined. You know exactly what are the cycle at the ground level, and so the sequence of cycle you get is unique up to a commutation of the cycle. There is no two different way to decompose a rearrangement as a flow. To decompose it a product of cycle, there is no two different way up to a commutation of disjoint cycle. Well, it's something subtle, this lemma, Cartier-Fouetta lemma. This is exactly one of the main theorem of the Cartier-Fouetta lecture note, which have been used we will see in physics. So let's do this for this. You see, here is a flow. This is a rearrangement. As a flow, this is the maximal edges. So you have three maximal edges. The red one going from 1 to 2, the blue one going from 2 to 1, above the blue point there is nobody, and the green one going from 3 to 2. You see these three maximal edges, and then these two maximal edges, these two, 1, 2 to 1, you get a cycle. So if you delete, you have a cycle of these two maximal edges, you delete it, this makes this cycle on the top of the heap, and then you remain these green edges. Now look what are the new maximal edges. This will give you another maximal edges because this point has been removed. So you get this is a maximal edges. This one is a maximal edges. Then you get a cycle. In fact, you get two cycles at the same time maximal. This one also is a maximal cycle. And you continue, you get this cycle. So you remove the cycle one by one in any order. You will get always the same.
Could we have that example again? So what's on top of this one?
On the top is so the edges, the maximal edges is edges in the big edges in red. 1, 2. These edges 2, 1. Because you see at the root of the edges there is nobody above. And this green one.
Doesn't this just contradict what we said? Yeah, it does. This is an example where you have a tree.
There is a tree.
Yes.
Tree.
So the exercise is solved. we get a counter example. So sorry, I am so used to do with geometry that sometimes I don't make any mathematical reasoning. I just look at the picture, and as the Greek people at the time say, maybe picture has false intuition. You should not do the picture. Let's do only calculus only. So this is the abuse of visual proof, you see, for me. So sorry, we have solved the exercise. So see, any rearrangement, you delete, you take off a cycle, then you get another rearrangement.
This is the product of cycles.
Yes. So this is the main theorem. You see the heaps. Any rearrangement can be viewed as a product of cycle. If you like better commutation monoid, any rearrangement is a product of cycle and up to the commutation of two disjoint cycles. If you prefer heaps, any rearrangement as a flow is heaps of cycle, which are put cycle which fall down. And as soon as two cycles have a common vertex, then one of the cycles is above the other one. So this is one of the main lemma. Yes? Storage, no?
No, so the correct lemma should be that if f belongs to rearrangement of this, phi should have at least one cycle. There, and no, that's all.
Yeah.
That's all.
Yeah, yes. If you have a rearrangement, then you can find a decomposition of rearrangement multiplied by a cycle. Or, if you prefer, to work at the ground level, cycle multiplied by a rearrangement. And then you apply recursively this, and you get decomposition as a product of cycle. And so this map, which I call G, it's a reverse of the map F.
You can get the generating function.
After the generating function, yes, of heaps of cycle. This will the next chapter will determine
So
that.
for induction hypothesis, you need only one cycle.
Yes, only one cycle.
In that open, nothing else is-
Oh, okay. So look above, you have an endofunction. Necessarily there is a cycle, because if there is no cycle, all the trees, the roots are rooted, there is no cycle rooted, so which means that you are, from the root of the tree, no edges are going outside. So it's obviously it's not a rearrangement, because some edges, one or several edges are getting inside, and nobody is getting outside. So just a remark for people who like exponential generating function and spaces. So, an arborescence, une endofonction on a set is a substitution of inside the species of permutation, you substitute an arborescence. This is a typical example of substitution of a species into another species. So this is an arborescence, you see, with the cycle and the trees. This is the image we have seen above a heap, which are more complicated because it was a partial arborescence. And you see an arborescence can be, you see in green you have some permutation. Here it's a permutation with the cycle of 4 elements. This permutation is a fixed point, and this permutation is a fixed point. So in green, you have a permutation on 5 elements. And imagine inside each vertex, you put inside an arborescence. Arborescence is the rooted trees. And then the construction, the rooted trees, you see, you put the trees in fixed to the cycle. And this is an arborescence. So this is a typical example of substitution of a species into another one. What we have seen with the logarithmic lemma was exponential of species. It was a substitution of some species inside the species set. Set means you do nothing. Here the species is permutation. I take a permutation, and each point of the permutation become a block of the partition, and in the block I put an arborescence. So this is a typical, you have this picture, you see, this, and this picture. So you should have the generating function should be the substitution of one into another in exponential form. So I finish this first part by exercise. We have seen that any heap is in fact a heap of subset, of non-empty subset. And similar exercise, any commutation monoid is isomorphic to a submonoid of a flow monoid, in fact, even a rearrangement monoid. I give you just a hint. Go back to the proof that any heap can be viewed as a set heap of subset. We define starfish, and if you go back to this the picture, then you will see, you will guess where are the rearrangement. Knowing now that rearrangement is related to cycle. And then we finish the class last time by bijection, by starting with defining a bijection between paths and heaps of cycle, with some condition, an extra condition. So let's take a path. A path is any sequence of points in a set X. It can be a graph if you prefer. So there will be some elementary step forbidden. In a graph, you have only incident matrix, but if you put a weight Aij equals 0 or 1, then you will select all the paths of the graph. So I can make the reasonment in any set, and a path in X going from U to V I am going to send by a map key to a pair eta E. So eta is a self-avoiding path going from U to V. And E is a heaps of cycle such that if you take the projection of MM is any maximal piece of the heap, the projection of this cycle must intersect eta. See, a heaps of cycle, it's any element of the heap, it's a cycle plus the level of the cycle. And the cycle itself is a projection of the piece. So if you take the projection of the maximal piece, they must intersect eta. Intersect means that alpha, the cycle and the path, has a common vertex. So it will be very useful when we work with weighted paths. All the paths will be weighted. Even path in a graph, it's weighted by 0 or 1 to have a lowered edges or forbidden edges. So if you have an extra property that if you take any pair ST of vertices, the number of times the edges ST appear in the path is the same as the total number of times the edges ST appear in the pair eta E. If you count.
Eta must be maximal, maximal also.
What means maximal? It depends what means maximal.
It is not. Okay.
The edges of eta will be maximal edges.
Okay. Edges of eta. Okay.
But you can say another formulation is to say, okay, I have heaps with two kinds of pieces. Cycle and self-avoiding walk. When I say walk, it's path. In physics, they say walk. In combinatorics, we say path. So we have two kinds of pieces. And you can say that eta E is a pyramid of such pieces with the condition that in the pyramid, there is only one self-avoiding path. There is not several self-avoiding paths, only one which is a maximal piece. And the dependency relation between self-avoiding path and cycle or other self-avoiding paths is that they are a common vertex. So it will be the same formulation, you see. You can make heaps of self-avoiding paths, heaps of cycles. You can mix all the heaps, and then, but there is at the top only one self-avoiding path on the top, and all the other pieces, the cycle, intersect the self-avoiding path with preserving the weight. So here is the image. You see below you have the blue path. I take continuous path, but imagine there are many vertices. It's a discrete path. You can take the limit. After the probabilist will take the limit, but this is another story, and we are in combinatorics class. So you have the blue path on the top, and then below you see there is a heaps of cycle. In red, I put the maximal piece. Here there is 3 maximal cycles, and each of these cycles intersect the blue path. They have common vertex. And all the other cycles, there are many cycles below. See, there's a lot of cycles. They intersect another cycle, or maybe they intersect the red cycle. Or maybe they intersect the blue path also. If you look above, but as a heaps of cycle, I have only the maximal piece, the condition, the maximal piece intersect the blue path. So some cycle like this one, you see, maybe they don't intersect the blue path, but they are below somebody which is going to intersect the blue path. Now here is the description of the bijection. So take your path omega, and I suppose I am taking time t the time 0, 1, 2, 3, 4. So I am going to follow the path, and I will define 2 things: the cut of the path at time t, and the heaps of cycle at time t. So the cut is a self-avoiding path. At the end, my cut will be the blue path. But you start at the beginning. There is no initial. So I would say, so at the beginning, as S0 equal with the cut, at the beginning, the cut is reduced to the point. The cut is only the single vertex S0, so it's a path. A path reduced to a point is a path, an empty path with length 0, but it's a point. And the heaps of cycle is empty heap. So this is the starting of the algorithm. Then at time t. If you know at time t plus 1. Suppose there is two cases. Suppose that this is the blue, the cut, the self-avoiding path starting from u until s index it, and you go to s index t plus 1. I put it because during the time the process is not necessarily s index t. S index t maybe have disappeared in the process. So first case, this edges here, the last edge I do, st plus 1, does not belong to the cut. So I am extending the self-avoiding walk. In that case, the new cut at time t plus 1 is the older cut plus followed by this new vertex, and the heap does not change. Okay? You start with at time 0, the cut is reduced to a point, heap is empty, and I suppose at time t I have my pair here. At time t plus 1, in the first case, the self-avoiding walk is increased by one more step, and the heap is invariant. Second condition, maybe st plus 1 is going to intersect the blue path, which make a cycle. In fact, a pointed cycle, because it touch when you know where it touch. So the new cut is you delete this cycle. So the new cut is only from S0 to Sk. And then the new heap, this cycle gamma, this pointed cycle, I forget the point, and I take the product with the former heap. So I put this cycle gamma on the top of the heap. So in fact, you see the pointed gamma is a pointed cycle with a starting at Sk, and the pointed gamma is all this cycle, and the last point is equal Sk. And then you continue like this. Your paths have length n, and at the end you get the path eta, which is the cut at times n, and the final heap is E. So this process is well known, in fact. In physics, it's known the loop erase process, or very often there are many, many papers on this. In physics, it's a looped erase random walk. It was defined by Lawler in 80, much older, 1980. And
Why it is random?
loop. Oh, that's the name, random, because you
You want to consider random paths in which you don't want to. Like,
You take-
It's a random path on X.
because we are in physics now. This is the if you see L, R, W, you are in physics, and they study suppose you have a big grid, 1,000 point by 1,000 point, and at each point you go by random. You go north, east, south, west, and then you go by random. So you have a random Brownian path. But if you delete all the loops, then what you get at the end is a self-avoiding path, which is supposed to be the so-called looped erase random walk. But the path you get, the path eta, is not at all a random self-avoiding path. Because this problem to find a random self-avoiding path in a certain lattice is very difficult. You don't know how to. But it was a process to get some random self-avoiding path. But the probability to get it is not the same as the probability if you take a random self-avoiding path with uniform distribution among all the. So we are here in probability. So all this story of erasing the loops is very, very well known in probability. There are hundreds of papers on this. It's very interesting. If I have time at the end, I will show you the complement, open a window on this probabilistic physics part. But the big mistake is to have erased all the loop. So there is many theorems which are difficult to prove because you forget all the loops. But our bijection, we keep the loops. But if you keep the loops, what you can keep is a sequence of cycle with pointed cycle. Each time a cycle falls down, if you remember the point where it falls down, if you remember the sequence of a cycle, So if you remember the sequence of pointed cycle,
But
okay, you can reconstruct the path.
But we are keeping non-pointed cycle.
But this is too much information.
But you also have to remember the order in which they fell out.
Suppose you remember this sequence here.
Yeah, as a
So you remember as a sequence
yeah, then it's fine.
the total order of cycle, and you remember the point. Then you can easily reconstruct the path.
But you only need the heap.
No, we need only the starting point and the order. That's all. We don't.
I
need the
repeat. What is obvious is that if you know eta,
We know the starting point.
you must know eta. If you don't know eta, then you are going to have problem.
Yes.
If you know eta, if you know all this,
Then it's okay. Yeah.
then you can reconstruct the path. You know eta, you know the sequence of point, you know the sequence of pointed cycle.
But
That is true, right?
we really don't need the pointer.
Give me the class. If I know all this, then I can reconstruct the path. Okay.
Yes.
Now, if I forget the point, I can still reconstruct the path. And if I forget in which order they fall down, but up to a commutation of disjoint cycle, then I can still reconstruct the path, and then I get a bijection. So this is why many people were close to this finding this, but there is few papers where this bijection is really written. It was written 30 years ago in French in some papers, and some people are rediscovering this bijection. It's a very powerful tool. It's not very well known, and with this tool, I realized that you can really do some. We will see that some problem on the loop erasing work can immediately be proved because you did not erase all the loop. You keep the heap, the key part.
So the heap is exactly.
The heap is exactly what you need to reconstruct all the information. And if you have sufficient power lemma on heap, then you can do some beautiful.
So then you can do random sampling of.
So I will put some research problem. If you solve it, I think it's easy with heaps. Then you can make a paper. Because all this story is not very well known, because I have the default not to publish. Many of these things I'm teaching are scattered in different papers, sometimes in French. They have been forgotten. So many things. So these classes is to really officially to publish as a video everything, and then so this is a very powerful tool, and you will see some application in all this class to many different topics. The application will be a very powerful tool for only the three basic lemma and some very easy principle. So let's prove the bijection. That key is the bijection. There's two different ways to prove it. First proof. Here is my pair eta E. So you have the self-avoiding path. Now it's in green. Sorry, it's come from different slides, and I don't read all the slides. So in green, you have the self-avoiding path eta going from U to V. Below it, you have the red cycle, the maximal piece. And below, you have some other cycle. So how to reconstruct the path? So here is the algorithm. Follow your path in green. And put in blue, the first time the path intersects the maximum cycle. So here, here, and here.
And 1 point we can have only one.
The first time the self-avoiding path intersect the support of the maximal piece. A cycle can intersect many times, you see. A maximal cycle can have many intersection points. What is the question?
1 point we can have only one outward arrow in the maximal. At one vertex.
No, the gamma is not part of the heap of cycle.
No, I'm asking the maximal.
Yes.
Oh, the other red is after removing this is the maximal. Okay.
The red are the maximal cycle.
After
Don't remove that. No, be careful. Don't remove them.
But gamma is something else. It's not part of the.
What is gamma? It's
Eta.
Eta. No, the green path is eta.
That is a
It was
different
blue.
piece of
So eta is above.
It is above.
You can see as it above or not, or below on the floor. That matters. Eta is somewhere
somewhere else.
in the air. But you have a heaps of cycle with 3 here on this picture, 3 maximal pieces. The red cycle. I define the blue point. For each red cycle, maximal piece, there is a unique blue point. It's the first time the eta, the green path, intersect. It must intersect. That's the condition of in the proposition. So this gives you a certain order in the cycle. First cycle, when you follow the path. First blue point, I have 3 blue points, which give a total order because they are order in the path. So the blue points give you a certain total order of the blue point, which imply a total order of the maximal piece. So I can say that this cycle is last in this total order. This cycle corresponds to the 3rd blue point. So this is the last cycle. Be careful, it's not the life cycle which falls down. And the last cycle maybe was not this one. So be careful. Be careful. We are going. So what happened now? If I go back, so this was the last edges. I am going to try to reconstruct the path starting from the 8 point. What I claim is that I can say that this edges has been the last part of the path. So these edges are, you start from the last point, you go back until the blue point of the cycle, and then you see on this red cycle, there is a last edges here. So I take this last edges and I claim that my path, the last part of the path was this. But this, I don't know, this edges, maybe was not the edges just before this one. Because maybe a cycle here, a small cycle fall down. When I read this part, maybe another cycle fall down.
But that would still be a maximal cycle.
Yes, it's a maximal cycle, but I have to break the cycle. This red cycle maybe did not fall down at all. See, it's fall down. No, it fall down, but it was. But the path I follow did not follow these edges of the red cycle in consecutive order. Maybe, maybe it follows some part of this red cycle. Maybe it do something else. Like here, see here, he was doing some other cycle, and in this brown cycle, he was doing something else. So maybe the path was going in many, many different points before going back to the red cycle. So what I can say is that this part was the last portion of the path. So I can delete it. Now I replace recursively. I have the same problem. I have a new green, new self-avoiding hook, which is the old one where I have added the portion of the. See, I take the red cycle. You take all the edges except the last one you have deleted. So the new self-avoiding path is this one. The new V now is V prime. And now there is maybe some new maximal cycle. Like this one. And of course, this new maximal cycle appearing must intersect this green part, because before they were below the maximum red cycle. Is it clear? No?
I don't follow this last cycle, the red one. That one. That one, I don't see why it may not be the last of third.
No, I did not express myself correctly. Okay. This red cycle was the last which fell down.
Which one?
Okay. But the path, the edges of the red cycle, maybe was split in different parts of the path. Because during like this one, when he was here, he was doing something else.
At some level, we can get something.
So what
maximally
below,
very.
Mm-hmm.
Something may have fallen down from
yes.
of that.
Mm-hmm. So what I claim is that I can say that the last part of the path was this. Then I delete this last part. I delete the edges of the cycle. So I have broken the cycle. I have a new self-avoiding walk. I am adding to the old one from this blue point. I am adding all this portion of the cycle except the last edges. And then I have so the new self-avoiding walk, a new V, which is V prime, and some new maximal cycle appearing. So there is the old one, plus the new one. And the new one, of course, they intersect the green paths which were blue before, the eta paths, the new eta paths, this cycle intersect because before they were not, in the previous, this cycle was not maximal. It was touching the right cycle, or maybe touching this part here. So this is the idea of the reverse bijection.
And you follow by induction.
And then by induction, you go back. So this it seems very easy. Rearrangement paths the same, but it's something which sometimes are not trivial, and you can make easily mistake, as I have done before. So I hope this proof is correct.
Yeah,
Think about it and tell me next time if there is some counterexample. But I have a second proof to be sure that always I have a second proof.
One proof can be wrong.
Yes, but two wrong proof, then it should be two proof is enough, I think.
So what happens in the next step?
The next step, then you continue the same.
So you delete.
So the new V is V prime,
So that's the end point.
new eta is this, and then there will be some new blue point. The new blue point, it will be, see, there will be this point, because new cycle are appearing, new maximal cycle appearing, so there will be new blue point, and again you continue to order them, to take the last one. So if you like programming and computer science, maybe give an algorithm to do this recursively. And check with the second bijection and make many examples and give me the confirmation that the two bijections are of the proof. So second bijection, it's so you take your path, take the pair eta A, so break everybody by the map F. So everybody on the left and the right part is going to be a flow, heaps of half edges. And lemma, if you follow the flow of this, so here we have a flow, follow the flow starting at S0, then you get back omega. So it's maybe a much shorter proof. And take your pair eta E, coming from the path by the map key, break everybody, all the cycle, all the edges, so everybody fall down and you get a flow. So you get a flow which is then starting from S0, you follow the flow, as we have seen in the first follow the flow, and I claim that you get following the flow when you are stuck, you reconstruct the whole path. As we have done before, when you have a single path, we break all the edges, we follow the flow starting from the initial point, and you get back the path.
So when you write it, FOV dot F of beta, which one is on the bottom and which is on the top? I just forgot. FE is on the bottom.
Yeah, left.
Yes. Eta is on the top, yes. And so corollary, if you have S0 equal Sn, so if you have circuit, U equal V, then what is the blue point? The blue path, the self-avoiding path, is reduced to a single point. So a set of heaps of cycle such that the maximal cycle intersect the path eta. They must intersect a unique point. So there is only one maximal piece. You cannot have several maximal pieces intersecting the same point. So there is only one maximal cycle, and this maximal cycle contains the starting point. And so you get the bijection as a special case. you get a bijection between circuit, path going back to the origin, and pointed cycle pyramid. It means it's a pyramid of cycle. There is only one maximal piece. And pointed means that stop cycle, there is a specified point.
That is the starting point.
And we know from the previous chapter that this is the t time, the derivative of the logarithm of the generating function of heaps of cycle. So this will be very useful for the other chapter we'll do on the linear algebra, graph theory, thermodynamic, Ising model, directed animal. Many things will be with this particular case. So an example with Dyck paths. If this one want to work.
Battery 100%. Connected to MacBook Air disabler.
Cannot stop this voice. So in case of Dyck paths, see I put the Dyck path like this. It's the projection of Dyck path on the vertical line becomes the projection on the horizontal line. So you start from 0, and then you see your self-avoiding path, you go here, and then I am doing a cycle. So your self-avoiding path in blue is going to be just a sequence of consecutive points, and the cycle which is going to fall down are only cycle of length 2, which in the following video it will be dimers. Cycle of length 2 is dimers, and
MacBook Air disabler. Disconnected. Ready to cut MacBook Air disabler. Connected to MacBook Air disabler.
I tried before and I don't know why this make me. Donc so the violinist is Gérard Duchamp. We have done several animation with him, and you have seen the bijection working in the special case of Dyck path. Cycle falling down are only length 2, so which I put as dimers. So if I want to go back to my notation of the proof of the lemma, I should reverse this like this, you see. And the starting point is here. So this was the correct, to be compatible with the notation of the general case. So you start from here, you see, you go here, and then the first cycle fall down, and then another fall down. So it was the first cycle falling down, second cycle falling down when I have done this. Then I go here, and then the cycle is falling down, this one, then this one, you see, and then here, the cycle fall down, etc. So you have your heaps of cycle, and it's a pyramid because you go back to the origin, so it's a unique point. So there's a unique maximal cycle which contains the point 0. So it's what we call a semi-pyramid, which are counted by Catalan number, and it's a number of Dyck paths. So there was some exercise to find a bijection between Dyck paths and Catalan. This bijection, I am sure, it's the same as the bijection you found before, probably. And now the reverse bijection. reverse bijection. Let's do it on this particular example, the reverse bijection in the general case. So what you have to do, I start from this, and I have to order all the maximal cycle below the self-avoiding walk. Here, the self-avoiding walk is reduced to a point. There's only one maximal cycle. So you take the last edges when it's get in. Take these last edges. So I know that this was the last point of the path, and this last edges, now this is the new self-avoiding walk. Now below it, there is only one maximal cycle. Take the last edges, which give me this is the last edge. Now this is a new self-avoiding path. You see, again, you do the same. So here there is no problem because below there is only one maximal edge. Here now you see there is again one maximal cycle. When you follow the self-avoiding path, take the first time it's this cycle. So I know the path, but I have to delete all this. And then this cycle is break into, this is what the last edge is here. So if you really think this is a reverse bijection in the case of the etc., etc. So here you see there is a possible problem because there is two maximal cycle. And you have to take, you see, what is, when you order the cycle from left to right, this one and this one are touching my self-avoiding walk. So which one I have to take? I have to take the last one. This is the first, this is the last one. So what you are going to do in this reverse bijection, so you take off the cycle. Each time there is several maximal cycles, you take the rightmost cycle. So what you get is a kind of what we have called lexicographic normal form. You are deleting the cycle one by one. There is a total order on the basic pieces, and you are taking the rightmost basic pieces. Sometimes we take the leftmost, sometimes the rightmost, but this reverse bijection is again a special case of the lexicographic order. It's very hot, huh? It's no air conditioning. Huh? You don't are warm here? So see, each time I am deleting the cycle, Deleting the cycle, I can reconstruct step by step my Dyck path, and when I have deleting two possible maximal cycles, then what you delete is the rightmost of the cycle. So it's exactly one of the bijection exercises you are supposed to find in the previous chapter, that to use the normal form, Knut normal form, or to use a lexicographic normal form to get a bijection between Heaps pyramid of diamonds and Dyck path. This is exactly the same bijection as bijection we are supposed to find in the exercise. So if you look carefully all of the slides, I claim that this is exactly a special case of the general bijection which we have seen for the general case. So you see so the total order of the cycle, 1, 2, 3, 4, 5, 6, this was the order, the reverse order in which they fall down. And this reverse order is exactly the lexicographic normal form of the Heaps of cycle. Okay, first exercise. For bilateral Dyck path, explicit the general bijection and its reciprocal. For bilateral Dyck path, then what would be the reverse process? So you can feel that you are going to get a pyramid. It's counted by half of 2 and 2n, and the reverse algorithm just it will not be the lexicographic normal form. It's something slightly different, but do the reverse algorithm and so some exercise which will be important for the solution of the Ising model with Heaps. and also to define the zeta function graph. Yes?
Could we just see the exercise once more?
So you take a bilateral Dyck path, which I have written like this. So you start, it's a path, you see, going when you are, is go to the next neighbor on the right or next neighbor on the left. Opposite to Dyck path, you can go always left or right. So I claim that, again, the cycle falling down are only length 2. What you get at the end is a pyramid of cycle of length 2, so which is equivalent to a pyramid of dimers. And the exercise is find the reverse bijection. Check that the reverse bijection, in the special case of this, take the reverse bijection in general, and this will give you a process to take off the dimers one by one in a certain algorithm, which will give you back in which order the dimers fall down. But each time you will not take the leftmost or rightmost cycle. It's something a little more, it's easy, but it's a little more, it's not so trivial that taking the leftmost or rightmost. So the exercise is when you have several dimers to take off in the reverse bijection, which one are you going to take? The second exercise, it's backtracking path or non-backtracking. So this will be important in different papers or different chapters of this class. So path make a backtrack when he is doing this. You have a consecutive sequence of vertex. It's from Si, Si plus 1, and again Si. It's an immediate return. You go do one step, immediately you go back. So exercise 2. I can make 2 conditions on the path. First condition, the path has no backtracking. We will need non-backtracking paths in different chapters of the class. So you can maybe in a naive way say, okay, if there is a backtrack, a dimer of fall down is falling down, and if there is no dimer unless 2 in the heaps, it's not backtracking. So we have 2 conditions, non-backtracking, second condition, and the heaps, related heap in the bijection key has no cycle of length 2. Exercise. Is it true that 1 implies 2? Is it true that 2 implies 1? Is it true, or find a counterexample? So I can tell you there is no way to characterize, because we have to characterize non-backtracking paths, and doing this will be not possible. Just looking the heap here, there is no way to characterize non-backtracking paths.
Certainly,
Exercise 3. This notion of tree-like path is due to Godzilla. So take a graph. Take a path on the graph. So the path gives you a pair eta E, and omega is called tree-like path if all the cycles have length 2. So this is a totally reverse of non-backtracking. It's always backtrack all the cycle, which means the definition of Godzilla was not using heaps and the bijection, but the definition was like in France we have the tale of the petit pousset. You know, a little kid is in a very poor family, and there is 12 kids in the family, and the father says we cannot feed all the children, so we are going to take them in the big forest, and we are going to lose them in the forest. But the petit pousset, he hears the parents in the night that they were saying we are going to be put in the forest and to be lost. So he took a lot of stone, and during the parents take all the children in the forest. So and each time he make a step, he put a stone. And then when he was lost, but if he if during the trip with the parents, if he crossed the same vertex twice, he said, oh, I am going to lost all these stones. So he delete, each time he was crossing itself, he take off the stone so that the path of stone from the origin of the house was always a self-avoiding path of stone. And when he finished, at the end, when he was lost, then he can, following the stone, he can go back to the origin. See, so each time you move, if you have in a new place you've never been, you put a stone. In case you are going to find one of the stones you have already done, so don't cross it because you are making a big cycle. So go back on your step. Go back on your step by taking again all the stone in your pocket. So each time you see, you make a new stone or you go back on your step. Never make any cycle of stone. So this is a tree-like path. If you are lost in the forest, think of the trees and you go back to the origin. So this is tree-like path. For example, Dyck path and bilateral Dyck path are tree-like paths. The trees, it's reduced to a segment, a long line. And each time you are on a vertex for the bilateral path, each time you have vertex I, then you go to I plus 1 or I minus 1. See, this is an image of a tree-like path. You see, you go like this, like this, like this, and then sometimes you go back on your step. So it means that, you see, you can go several times on the same vertex, but each time you can imagine that you are connected to your origin by a sequence of stone. Between two stones, it is an elementary step. When you arrive at a place where there is already a stone, you don't go on the same stone, so you are going to make a cycle. So you go back to your step by collecting your stone. But each time you go back on your step, you take off the stone. So each time you put a stone in your pocket, means you are making a cycle of length 2.
So those are the...
So tree-like path in the bijection between pair self-avoiding walk and cycle is exactly when you move on your grid here. Else you make a new, you go to a new vertex you have never visited, or else you go back on your step by collecting the stone you have put. So you are always connected from the origin by a self-avoiding sequence of stone, and you always, else you put a new stone on a new vertex, or else you go back on your step by collecting the stone where you were fixed. So the exercise is the following. Give a graph with a vertex S. Try to construct a tree T. There exists a tree such that the tree-like paths on the graph starting at S are in bijection with the path on the tree. The path on the tree starts at the root, and the bijections, the length of the path are preserved. So when you do tree-like paths on the grid, you see it's in fact moving on the graph is the same as moving on the tree.
It may not be a binary tree.
No, it will not be a binary tree. It's a general tree. Huh? Maybe there is several.
But it's a rooted tree.
Rooted tree.
Is it a spanning tree?
No, oh, no, not at all.
Find a tree. So for every graph,
For
give
every
a
graph,
construct a tree.
you give a vertex of the graph. Huh?
Yeah.
You give a vertex, and all the tree-like paths on the graph starting from this vertex are in bijection with the path of the same length on a certain tree starting at the root. The tree...
It's not a subtree of...
No, not at all. It's much bigger.
Okay.
No. Construct a tree.
Okay. Then
Mean construct from...
I
No. The tree is very big. The tree is going to be, if you take a graph with n vertices, the tree maybe have a quadratic number of vertices. It's big. The tree is much bigger.
So it's not like looking at the fundamental group or the covering space of the
fundamental group or what?
Covering space.
Covering space.
Space maybe not. Maybe infinity.
right.
It's a finite space.
So maybe it's 325. There is no classes after. Maybe I should finish with something beautiful. So I'm going to put this in further lecture, and I will finish the 5 minutes with some complement. So let's. Here is a tree, right? Big tree. It's not the same as the exercise. So I go back to this loop erase random walk. The connection. So this is complement, means I'm going to open the windows on some things which are maybe you will not understand. I will not give definition, just to give you an idea. So loop erase random walk, you see, it's you take a random walk, like for example, take the lattice, a square 1000 by 1000, go to the next neighbor by a random walk with probability 1, 4, 1, 4, 1, 4 in the 4 direction. Then you will get, by doing the loop erasing, you will get a self-avoiding walk. And the physicists, the probabilists, were interested by finding by the probability law on this path eta. It's a way to construct self-avoiding walk. And for example, if you start from a point and you go like this, so you erase all the loops after n step, and you look, if you make a big circle, how long it takes to get outside of the circle. And by some physics or probabilistic theories, the average length of this, when you get outside, will be n power f5 over 4. It will be the average length of this loop erased random walk. And this is very interesting problem, because this pass in what is called the scaling limit. If you know all this in probability, the scaling limit is something, it's an SLT, so it is very famous Schramm-Loener evolution, etc. It's many, this was a big discovery at the beginning of this, in about 2000, that this kind of model, SLE, so there are many hundreds of papers on this. So it is very connected with very beautiful physics and probabilistic mathematics. And this problem of the distribution of this loop erase random walk is related to the abelian sand pie model, when some sands are falling down on the square, and it's related to the dimer model, and it's related to the spanning tree model. The problem is you take a graph, give an efficient algorithm to choose a spanning tree with uniform probability. So there is two amazing facts. That if you take this path with the loop erase law, the loop erase distribution, and people were surprised that if you take the reverse path, it will be the same law, the same distribution for the reverse path, which is not obvious. It's not obvious at all from the definition. If you have a probabilist, I see some proof. There is 4 or 5 proofs. You have to go to the Laplacian. You have to go to harmonic function. No, it's not trivial at all. That the distribution of eta from U to V is the same. When I say distribution, I'm not going to define all this probabilistic word. The law, the probability law of eta from U to V is the same as from V to U. Now, what we have a very easy proof. Look, for example, if you take this path going from U to V, if I take the bijection, if I take a loop erase process, it gives you this. One cycle is deleted. If you go in the reverse way, it gives you this. So when you erase a cycle, it's very deep, the connection between erasing in one set and erasing in the other side. But now, if I make a formalization of the probabilistic, is the following formalization. You have a graph, you have a valuation going from I to j, you have some paths evaluated, and what is the problem? Is that you have a path omega, you are erasing all the loop, give you a self-avoiding mode eta, and what you have to compute is the weight of eta will be the sum of all the weight of the path omega going from u to v and omega giving eta. See, the weight will be probability. If you are on a grid, 1, 4, 1, 4, 1, 4. If you are on the border, it's not 1, 4, 1, 3, it's different, but the weight will be probability, and what you have to compute, the distributive probability distribution, is the sum of all this. So you have to take the sum of the weight of all the paths omega from u to v, giving the path eta. But now we know that such paths going from u to v are in bijection with this. Now, reversing eta. But there is a trivial bijection between paths giving eta and paths giving the reverse eta. You keep the heap and do the reverse bijection of the reverse eta, but the same heap. There is a trivial bijection. So you have to do the reverse bijection eta, but for the same heap of cycle. So it's going to be totally different. But the weight is preserved, and this gives you a proof that the same distribution. Because there is bijection from one path to another path. But if you delete all this cycle, you put all in the trash. But now we have to save energy. We don't have to put everything in the trash. So the advantage of such proof is organic combinatorics. Organic means I keep all my cycle. This was a mistake, to put all them in the trash. So keep them. Don't waste. And if you keep them, then you keep the whole information. But to keep them, you need a heap. Not a trash, vulgar trash. You need a heap. And if I keep them, then this proof can become obvious. Because the bijection from path to path, you keep the heap, reverse the path eta. Now the second amazing fact is that if you take a graph, take a spanning tree. Spanning tree means you are selecting edges such that the whole vertex covers the graph. So take a spanning tree with random distribution, which means that each spanning tree of the graph is going to appear with the same probability. And take any vertex u and v, and there is a unique path in the spanning tree going from u to v. Okay? So the second very amazing fact is that the distributive law, probabilistic distributive law for the path uv is the same as the distributive law for a loop erasing walk. So you have from u to v. In the graph, you do a loop erasing path, which gives you a certain probabilistic law. And this is the same as taking a random spanning tree with uniform probability. The path going from u to v in the tree is fixed, and both processes give you the same probabilistic law. So this is really amazing. And here is an example of a grid. Here is the spanning tree of the square lattice, where you go to the next neighbor. Here in red is a loop erasing, is a walk in the trees going from one corner to another corner. And the path you get would be the same as you are taking by random a loop erasing random walk. But can we prove this with heaps of pieces? Let's go back to the homework. What you see above a path. What you see above a path, now with the bijection, it's a self-avoiding walk going from u to v, and the arborescence, there is no cycle. So it's a self-avoiding walk plus some trees. In fact, it's a spanning tree of the support of the walk. When I look above a path, so I have a spanning tree of the set of vertices where the path is going through. And so the research problem number 1. Can you prove the equivalence between uniform spanning tree and taking a path in the tree and the loop erasing walk from U to V using heaps of pieces? Now maybe I don't know. This was an idea I get the last few days. If you take these trees, take a path omega, take the pair eta e, then look above the heaps and the eta, you get a trees, and you get in fact a spanning tree of the support of omega. So question: is it a random spanning tree for the graph formed by the support of the path? If yes, then I have proved my second remarkable fact. I don't know. This is a research problem. Use the heaps. If you solve it, then you make immediately a paper. If it's random tree. And I will finish with an animation to show you how it works. So there is an algorithm of Wilson. There is something stronger than what I say. Algorithm of Wilson. You take, I am going to construct a random tree on this grid. You take a total order on the vertices of the graph or of the lattice. You start from a point. Start from the point x1. Then you go by random. You make a random path, random Brownian path, but loop erase. You take off all the loops. And certainly you will go back near the red point. So when you go back near the red point, then you delete these edges. You have a self-avoiding path. Then take any point here. Take a random loop erasing walk. And then you will touch, as soon as you touch previous part, you stop. And again, you choose another point. Take a random loop erasing walk. And continue like this. And you will get a trees. And Wilson algorithm tell you that the trees will be by random. So here is how it works, this algorithm. Oop. I have no connection. I have to connect to the Wi-Fi. It was connected before, but oh, please, I have to look the second screen. Can you give me the second screen, please? Yes. So now it should work. Okay, so here is the algorithm. Oh, it goes so fast. Sometimes it's slow. Maybe I repeat it because sometimes it goes so, not so fast. So see the seed. You start from taking the vertex at the right bottom of the one vertex. Then you take a loop erasing walk, like this one. And each time it touches the trees, it's amazing. Usually it don't go so fast. So in red, you have loop erasing walk. As soon as they touch the tree, here is the trees.
So where do you start the new one?
At the small, so you start here.
The first I start.
See, here you see the white point here.
Yeah.
That was the starting point.
It always starts.
Then it is a random loop erasing walk, and you have to wait until it touch the point here. So here you are going to wait a certain time. See, the point of the lattice are ordered from right to left, from bottom to top. So we are waiting until this path It's a loop erasing work. All the loops have been deleted.
So the initial
Or it should take a few minutes. If you are patient, then it should. You see, each time it's a loop erasing work, and as soon as it touches the white part, then it will keep the white part, and then again start again. You see, again. And once you have touched, you see, but now it's going to be very fast. See, it's looking, as soon as it touches the white part is the trees. When you will touch it, then you keep the loop erasing work.
But you never.
Almost, yes, touch. And when it begin to touch, then it go, you see, and then at the end it go very, very fast. And you get a random.
But each new path doesn't start at a random point, does it?
Eh?
Where does the next path start? After it touches, it starts at the same point when.
You see, no, you see.
Maybe on the slide it's easier to see. Wilson.
Yes, that's I showed you on the slide. So see, you start in this algorithm. He was starting from this point x1. Then you go and you get as soon as you go back to the origin, you keep the path, and then you take the next point on this. So the point where order like this, and then the next point on the second line. So in my example, I take the point anywhere in the. I take a second, but you can take the point anywhere. You have a total order on the point of the grid. Once you get like this a certain part of the tree, then take any point, do a loop erasing random walk. As soon as you are touching the tree, you stop and choose another point, like this.
But you need to have a total order on the.
Yes, you have a total order on the point of the grid. In this example, total order was from right to left and from bottom to top.
And the result is a uniformly.
And the result is a uniform spanning tree. So this animation was due to Mike Rostock on this, and I will finish this with research problem number 3. So if you take a random path, instead of deleting all the loops, the loop erasing path, why not to keep the top edges in the bijection between the path and the pair of self-eroding paths and the heaps of cycle. If you keep all the top edges, we have seen that what you see above is a spanning tree. So my question, what you get at the end, when your random path has covered the whole vertices of the graph, do you get a random spanning tree? And then compare, if it's true, compare this, I call this organic algorithm, because instead of deleting all the loops, you keep not all the loops. For the bijection, you need to keep the total number cycle, but you keep only the top edges. So if you keep these top edges, then this gives you trees. If you keep it constantly by renovating the top edges, does it give you a random spanning tree? And if yes, probably it's much more efficient than this algorithm. Because you have seen this algorithm at the beginning, it's throwing away so many loops. But if you keep some part of the loop, maybe this will be better algorithm. But the problem, I don't know if I get a uniform random spanning tree like this. Or if not, what is the probability? So this is a research problem for people algorithmic or liking probability. Okay, thank you very much.